Hello everyone. Welcome back to our mathematical adventure. Now, tell me this. Have you ever seen the beam of a torch, the orbit of a planet, or even the curve of a car headlight and wondered, why do these shapes look so perfect? Well, surprise. All of them belong to one big mathematical family, the conic sections. In the previous chapter, we played with straight lines, the simplest geometric forms described by linear equations, things like y equals mx plus c. But today, we are leveling up from lines to curves. These magical curves, circle, ellipse, parabola, and hyperbola, are all born from just one shape, a cone. And no, not the ice cream kind, though that's way more fun to eat. We're talking about a double-napped right circular cone. What's fascinating is that by simply slicing this cone at different angles, we get completely different curves. And guess what? A Greek mathematician named Apollonius, way back in 262 BC, actually gave these curves their names. Yep, over 2000 years ago, geometry was already this cool. So, fasten your seatbelts, because we're about to slice through cones, literally and mathematically. Alright, let's start at the beginning. Imagine a fixed vertical line, call it L. Now take another line M that meets L at a point V and stays tilted to it at some angle alpha. If we rotate this line M around the vertical L, keeping that angle alpha constant, the surface we get looks like a beautiful, smooth cone, like a party hat turned upside down. This cone actually has two parts, the one pointing up and the one pointing down. And together, they're called a double-napped right circular cone. The line L is the axis, M is the generator, and V is the vertex. This cone is our parent shape, the mother of all conic curves. And the best part? We are going to create all our famous curves just by slicing this cone differently. Geometry really is like cooking. Same ingredients, different recipes. So what exactly is a section? Well, if you take a cone and cut it with a plane, a perfectly flat sheet, the curve formed where the plane and cone meet is called a conic section. Now here's the twist. The shape of this curve depends entirely on how that plane is tilted. If the plane cuts across the cone straight and evenly, boom, we get a circle. Tilt it just a bit, we get an ellipse. Make it parallel to the generator of the cone. Out pops a parabola. And if the plane slices through both naps, we get a hyperbola with two opposite branches. And if the plane passes right through the vertex, oops, we get degenerate conics like a point, a line, or two intersecting lines. So, yes, how you slice it really does matter. It's kind of like cutting a watermelon. Depending on your knife angle, you get circles, ovals, or if you're careless, a mess. Now let's classify our four main conics one by one. Circle, when the cutting plane is perpendicular to the axis of the cone. Every point on that circle is at the same distance from the axis. Ellipse, when the plane cuts obliquely through one nape at an angle smaller than alpha, the angle between the generator and the axis. Parabola, when the plane runs parallel to a generator of the cone, we get an open curve extending infinitely in one direction. Hyperbola, when the plane slices through both naps, forming two opposite open curves called branches. And if our cutting plane passes right through the vertex, we get degenerate cases. A point, a single line, or two intersecting lines. So, depending on the plane's tilt, we travel through the full conic family tree. Circle, ellipse, parabola, and hyperbola. See, the cone is like a magician's hat. Every angle gives you a different trick. Alright, let's bring in a bit of algebra to see how geometry turns into equations. The equation of a right circular cone can be written as x squared plus y squared equals z squared times tan squared alpha. Now, suppose a plane cuts this cone horizontally at a height z equals h. We substitute z equals h into the cone's equation. That gives us x squared plus y squared equals h squared times tan squared alpha. This is our equation 1. It represents a circle in the plane z equals h, with radius equal to h times tan alpha. When h equals 0, the circle shrinks to a single point, the vertex of the cone. So we've just proven that a horizontal cut across a cone gives a perfect circle. Alright, let's wrap it all up. We began with a simple cone, a double-napped, right circular cone, and discovered that by slicing it differently, we could create every conic curve, circle, ellipse, parabola, and hyperbola. We saw how geometry leads to algebra, that the same shape can be described by a beautiful equation like x squared plus y squared equals h squared tan squared alpha. And finally, we explored how these curves shape our world, in orbits, lights, signals, and lenses. So, one cone, 4 masterpieces of mathematics. Not bad for a simple slice of geometry, right? And that's the fascinating story of how conic sections are born. In the next video, we'll dive deeper into how different planes produce these unique curves, starting with the detailed geometry of sections of a cone. See you there.